Welcome to lecture number 12 for ECE 321 Analog Electronics, Transistor Amplifiers. For the next couple lectures, we're going to be switching gears. We're now going to be looking at how to design an amplifier at the transistor level. This applies directly to communication circuits, but it's also kind of useful to see how amplifiers work. So a little bit of background. This is the circuit that we've been looking at quite a bit. It's a transistor. I can use that as a switch, or in this class as an amplifier. I've got the base current and the collector current and RC. If I draw the load line for the circuit, it looks something like this. When IC equals 0, I've got 11 volts base to emitter. So this right here, or collector to emitter, that's VCE. I'll be right here, 11 volts when the current is 0. When the voltage is zero, I'll have 11 volts over RC. And suppose that's like 54 milliamps. As I vary the base current, I move up and down the load line. What we did back in digital electronics, I either want to operate here, that's when the transistor is off, or here. This is when you're saturated. The nice thing about these 2 points is the power dissipated is 0. Power is volts times amps. If the current is 0, power is 0. If the voltage is 0, power is 0. So you can use a very small transistor like the 3904 transistors, kind of small like this with 3 leads. It's not designed to dissipate any heat. That's a digital transistor designed for digital logic, designed to be used as a switch. In this class, I want to operate as an amplifier. So instead, I want to actually operate over here in the analog region. So suppose I had IB is nominally 20 or 100 microamps, so that IC is nominally 20 milliamps. This is my nominal operating point. If I took the base current and varied it as a sine wave, so it goes 100 plus or minus 50 milliamps, that's what's happening to the current. The voltage then will vary between 5 volts and 9 volts. That's your voltage amplification. That converts a small current at the base into a large voltage at the collector. That only works if I'm in the active region. So in 321 analog electronics, I operate in the active region. You can kind of tell which transistor is which. In the active region, I'm dissipating a lot of heat. For example, right here, I've got 6 volts at 25 milliamps, whatever that is. 150 milliwatts. This is going to get hot. So likewise, the transistors designed for analog electronics tend to have a big heat sink on it. They're the TO220 package that looks like this, and typically this is the base, collector, emitter. The base they don't put on the middle for some odd reason, but they don't. This would be like the 6144 transistor that's in your lab kits. It's an NPN. So the generic transistor amplifier looks like this. What I've got is a transistor, of course, plus I have RC. What RC does is that is a current-controlled voltage source, or converts current to voltage. So here's your base current, IB, that gets amplified, creating IC. To convert current to voltage, I use a resistor. The purpose of R1 and R2 is I've got to bias the transistor in the active region. Again, on the load line, I don't want to operate here or here. I want to operate somewhere in the middle of the active region. That's what R1 and R2 do. They provide a DC offset and a current offset to turn on the transistor. The purpose of RE is to stabilize the Q point. So all this sets the DC operation of the transistor. That's going to take a lot of effort. And once I set the DC operation, I don't want to change it. For example, if I took this point right here and connect it to a sine wave, I just changed the DC operating point. I changed the circuit's operation. So I don't want to do that. So instead what I do is I couple the circuit with capacitors. One at the base, one at the collector, one at the emitter. So at DC, this circuit's completely isolated. That sets the Q point. To add an AC signal to it, I'll take one of these, make it the input. Like the first one we're going to be looking at is the common emitter. So this will be Vn. The collector will be the output. And the one I'm not using is tied to ground. There's three types. I could tie the emitter to ground, base to ground, or collector to ground. That gives me three different amplifiers: common emitter, common base, common collector. So in the coming lectures, we'll be analyzing all three of those. So you really have two types of analysis. I've got the DC analysis that sets the Q point, sets the DC operating point, presumably in the active region. And then the AC analysis, take this, connect this to a sine wave input, and then at DC, this has no effect, capacitor blocks it. At AC, the impedance is 1 over j omega c, is say if this is minus j1 ohm, and this is 10k. 1 ohm relative to 10k is basically 0, ignore it. What happens is the voltage at the base is normally something, plus a small AC signal. The AC signal is from your source. So that's what we'll be doing for the next couple days. To start out then, for this lecture we're looking at the DC analysis. The DC analysis is find R1, R2, and RE to set the operating point. RC is usually given. That's how much current you want to output, what voltage you want to output, what you want the output impedance to be. Solve for the other three. Then the AC analysis will be, now take one of these tied to ground for the common emitter, common base, common collector. Add an AC input in, find the AC output out. That's a small signal, meaning AC model. Do the AC analysis. That comes up later. It'll be in this course, but a couple of lectures from now. So let's start out. Analyzing the DC operation. Now at DC, kind of one trick is at this point, looking left, I see R1 to 12 volts, R2 to ground. So that's what this looks like. This is your 12 volts. At this point, VB, I see R1 to 12 volts, R2 to ground. Replace this with a Thevenin equivalent. So looking left, what I see is a Thevenin voltage, a Thevenin resistance. The Thevenin voltage is just by voltage division, R2 over R1 plus R2 times VCC. The Thevenin resistance is you turn off the source, and I have R1 in parallel with R2. So what I can do is get rid of R1, R2, replace it with the Thevenin equivalent, and that would be 5.33 volts and 222K. Now back in circuits 1, you covered Thevenin equivalents. This is where they're actually useful. It's the same circuit, equivalent, but the Thevenin equivalent is much easier to analyze, and we'll see that in a sec. Once I get the Thevenin equivalent, redraw the circuit. So again, I had the Thevenin equivalent up here, 5.33 volts, 220K, diode to ground. This is assuming R equals 0. And then I've got the RC going to 12 volts. So what that looks like is I have my 5.33 volts going to RB. This is VB right here. VB goes to the emitter, which is tied to ground, through a diode. The emitter is tied to the collector through beta IB. Collector is tied to 12 volts through 1K resistor. So that's the same circuit, and that's kind of one trick in this class. If the circuit's confusing, redraw it. A lot of times it's a lot simpler if you redraw it. Now to analyze, over here I know this voltage, that's 0.7 volts. Voltage drop across the silicon diode. So IB is just 5.33 minus 0.7 over 222K. This is 20.8 microamps. I know the collector current is beta IB, so this is 4.17 milliamps. And I can find the voltage. That's 12 volts minus 1K times IC, 7.83 volts. So on the load line, this is where I'm operating. This is 12 volts. I'm at 7.8 volts. And 4.17 milliamps. Second case, suppose the emitter resistor is bigger than 0. In that case, what you have is, again, you got your VBB, RB transistor, emitter resistor going to ground. And here's RC going to 12 volts. At the input, I have your VB, RB, goes to the base. Base goes to emitter through a diode. And now instead of being tied to ground, the emitter goes to ground through RE. Emitter goes to collector through beta IB. Collector goes to VCC through 1K. So there's the circuit. Now to analyze, if I sum the voltages around this loop to 0, well, I'll first define this current as IB. This current is 200 IB, or IC. Going around this loop, VBB is equal to RB times IB plus 0.7 plus RE times IB plus IC. And IC is beta IB. Solving for IB, I get this. It's your VBB minus 0.7. That's the voltage driving the current. And the resistance is RB plus RE times 1 plus RE times beta. 1 plus beta RE. So that's the base current. Once I know the base current, I can find the collector current. That's beta IB. And then VCE is your 12 volts minus RC times IC minus RE times IB plus IC. With the constraint that VCE has to be between 0.2 volts and 12 volts. If it's more than 12 volts, it actually clips at 12 volts. IC can't go negative. If it tries to go negative, it'll go to 0, and I get 12 volts across it. And VCE can't be less than 0.2, because that's when you saturate. If it's less than 0.2, this doesn't work anymore. I just saturate. This is 0.2 volts, and you have to reanalyze the circuit. Typically, I don't have these two cases, because if I'm saturated, it's not an amplifier. If it's turned off, it's not an amplifier. It's got to be in the active region to be an amplifier. So if it's designed correctly, I'll have this condition. If it's designed incorrectly and you're saturated or off, either you made a mistake in your calculations or this is not going to work as an amplifier. You need to change the circuit. That's analysis. In terms of design, again, I've got my load line. This is your VCE, IC, my load line. This point is 12 volts. Oftentimes I want to operate right here at 6 volts. The reason being is that allows my voltage to swing up and down by 6 volts without saturating up here or turning off. That gives me the maximum swing. Design would be kind of going backwards. Instead of given the resistors, find the operating point, this is given the operating point, find the resistors. So suppose I want the operating point to be 6 volts, meaning I want IC to be 6 milliamps. If IC is 6 milliamps, then IB is 6 milliamps over beta, 30 microamps. And find VBB, RBB to make this 30 microamps. Now, problem I have two equations, one equation, two unknowns. So somebody's arbitrary. A simple solution would be let VBB be 12 volts, because this is your R1, this is your R2. If R2 doesn't exist, I can just use a single resistor and make VB 12 volts. Then solve for RB. Again, I want this to be, 30 microamps. and I get something for RB. Converting back to R1 and R2. R1 in parallel with R2 is RB, and so I know R2 is infinity, R1 is 377K. VB is R1 over R1 plus R2 is 12 volts. Tells you R2 is infinity, R1 is 377K. This makes it kind of easy, converting back to R1, R2. The problem with that design is it's really sensitive to variations in beta. For example, if I built this in Circuit Lab, I designed for 6 volts right here. If I simulated, I'm getting 7.38 volts. The reason being is that I designed for beta of 200. If you solve in Circuit Lab, I find IB, find IC, and I can do that just by clicking at the base, clicking at the collector. It'll tell you what the currents are. Take the ratio. Circuit Lab uses a gain of 153, not 200. That's actually valid. If you look at the data sheets for a 3904 transistor, the current gain, HFE, some textbooks call it beta, some call it HFE, depends on your textbook. This says that the gain is somewhere between, minimum gain is somewhere between 40 to 30. Under this operating point, the minimum gain is 100, maximum gain is 300. So the gain is somewhere between 100 and 300. There's a lot of variation in beta. So what we assumed 200, the middle number, is perfectly valid. But Circuit Lab assumes 154 is perfectly valid. And that's typical for other transistors. The gain varies quite a bit. That's just due to manufacturing tolerances. In addition, the gain varies with current. If I look at the current at the collector on the bottom graph, beta varies between 120 to 160 and drops down to about 60. So beta is going to vary quite a bit. That's a problem because if I built a whole bunch of these circuits, I'm going to have a lot of variation in the Q point. This is called a Monte Carlo simulation. What I'm going to do is I'm going to pick a random value for the resistor. Again, what I've got is this circuit. So here's my transistor. Going to ground. Here's your RB. Here's RC. Here's 12 volts. Suppose these resistors have a 1% tolerance, and beta is between 100 and 300. What are you going to get for the actual operating point, the VCE and IC? Monte Carlo says, let's run build 100 circuits with random numbers. And MATLAB, let's see, where's MATLAB? If I type in the number rand, that generates a random number between 0 and 1. So every time I do that, the answer is between 0 and 1. If I do rand times 2, that's a number between 0 and 2. Rand times 2 minus 1 is a random number between minus 1 and plus 1. So if I do random number times 2 minus 1, times 0.05, there's 5%. And do 1 plus that. This is a number at 1 plus or minus 5%. It'll go between 0.95 and 1.05. That's your resistor, plus or minus 5%. So I'm going to take RB, make it plus or minus 1%, RC, plus or minus 1%, beta is 200, plus or minus 100, meaning between 100 and 300. From those, calculate IB, calculate IC, calculate VC, and plot them. Here's what you get. If I built 100 of these circuits, this is the distribution. The current, or the Q point, is sent anywhere in here. This is a problem because if I add an AC signal to it, sometimes I'm going to clip on the high side, sometimes I'll clip on the low side. The variations in beta are what's killing me. And right here, this is beta is 200. Circuit Lab used 154, so it gave me a different point. And it's going to vary all over here. That's the problem with the previous design. To reduce the effect of beta on the cue point, I add the emitter resistor. And this kind of adds feedback. If beta is larger, I get more current, which increases the voltage of VE, which reduces the voltage, the current at the base, which reduces IC, kind of a negative feedback. This helps stabilize the cue point. And to see that, if you go through the equations, for this circuit I can calculate IB. Going around this loop, minus VB is RB times IB plus 0.7 plus IB plus IC times RE. Solving for IB, I get this equation. Now suppose that 1 plus beta RE is much, much bigger than RB, then this term goes away. IC is beta times IB, so if I multiply by beta, I get IC. If beta is large, like 200, 201, 200 over 201 is roughly 0. They cancel. And now IC is independent of beta. It's just BB minus 0.7 over RE. That's kind of what you do to stabilize the cue point. The condition to stabilize the cue point is pick RE such that 1 plus beta RE is much, much bigger than RB, or actually kind of conversely. Pick RB to be much, much smaller than 1 plus beta times RE. So I don't really want to have RE. What RE does is, if this is a 1K resistor and this is a 1K resistor, let's see, half the voltage is lost through RC, half through RE, or maybe a third, a third, a third. So on the load line, this is your ECE. This is going to be maybe a third of the voltage right here. Here's a third and 2/3. This will be my cue point. This is your VE. I'm going to add a capacitor at this point so VE stays constant. So when I have an AC signal, this will go up and down. I want RE to be small because the bigger RE is, the bigger I eat up the load line, the more the load line I eat up. But I don't want it to be too small because then I can't pick RE, pick RB. If RB is too small, like 1 ohm, I've got a big power sink. The way you create RB is 2 resistors from 12 volts to ground. If this is really small, I'm sucking a lot of current, draining my battery. So I want RB to be large, meaning RE should be large, but don't eat up too much of the load line. So kind of a trade-off is pick RE to be RC or smaller. That'll eat up a third of the load line or less. Once I pick RE, pick RB to be much, much smaller than 1 plus beta RE. That'll stabilize the cue point. So as an example, let's go back to this circuit. I picked RE to be 100 ohms. This is going to eat up, maybe 10% of the load line. Find R1, R2 to make the cue point 6 volts and stabilize it for variations in beta. Now the first one, to stabilize the cue point, I need 1 plus beta times RE to be much, much more than RB. Beta is 200, RE is 100, so RB is much, much smaller than 20K. So let's make it 2K. Again, I'm not going to make it too much smaller because this affects what R1 and R2 are. If I make RB equal to 2 ohms, this will be something like 1 ohm. 12 volts across 1 ohm is 144 watts. I'm dissipating a lot of heat. So make this large, but not too large. And a common trade-off is just make it 10 times smaller. From before, IC is 6 milliamps. IB is 30 microamps. Going around that left-hand loop over here, so this was your RB, that's 2K, this is 0.7 volts, this is 100 ohms, this is your VB, and that's IB. From before, IB is VB minus 0.7 over RB plus 1 plus beta times RE. That's 30 microamps. I know RB is 2K, solve for VB. VB is 1.36 volts. So that's your Thevenin equivalent. What that tells me is that R1 in parallel with R2 is 2000. By voltage division, R1 or R2 over R1 plus R2 times 12 volts is 1.36 volts. Solve. And there's kind of one trick to solve. Let's divide by 12 and pull the R1 outside. R2 over R1 plus R2 is this guy. So I can substitute. This is equal to 2000 over R1. So I can solve for R1. R1 is equal to 12 over 1.363. That ratio times 2K. And kind of figure it's going to be the ratio. Your 12 volts to VBE. R1 is going to be bigger than R Thevenin, because these in parallel give you R Thevenin. R1's got to be bigger than it. So take the ratio that's bigger than it, 12 over VB times 2K. That gives you R1. R1 is 17K. I know that R1 in parallel with R2 is 2K. So solving, I get R2 is 2.2K. There's my circuit. I can now go into Circuit Lab, or actually go into MATLAB. If I redesigned it, say here's our R1, R2, RC, RE, beta, recalculate the voltage at the base, the current, and plot it. 100 points, the resistors are plus minus 1%, beta is between 100 and 300. Now here's the variation in the Q point. It's not zero. If I made RB 100 times smaller, this would be a smaller variation, but I get more current draw. So that's not too bad. That's what RE does. It reduces the variation of beta on the Q point. In Circuit Lab, if I redesign it, here's your 100 ohms, R1, R2. You simulate it. I designed for a Q point of 6 volts. I actually got 5.6 volts. Again, a little bit different because beta isn't 200 in Circuit Lab, but it's pretty close to 6 volts. Essentially, RE stabilized the Q point. So in summary, for a transistor amplifier, you have DC analysis and AC analysis. This lecture looked at the DC analysis. In order to use a Class A amplifier, basically what we'll be doing in this class, I need to bias the transistor in the active region. That's you've got your load line. I want to make the operating point somewhere in the active region, in here. The purpose of the resistors is RE helps stabilize the Q point. I want to pick RE to be bigger than 0 and less than RC. Purpose of R1 and R2 is they set the Q point and stabilize the Q point for variations in beta. So you kind of have two constraints. I want to pick 1 plus beta times RE to be much, much bigger than RB. That stabilizes the Q point. And pick RB and VB to set the Q point wherever it is you want, somewhere in the active region. So that was this lecture, DC analysis. The following lectures will look at AC analysis of this circuit.